Hi everybody, this is Dr. Chantel Marshall once again, here to go over some practice problems for the t-statistic for independent samples. So let's begin with just some numbers. Often what you're doing is trying to figure out what's going on for a specific hypothesis, but I'd like you to get some practice with just looking at two groups of data. This is the first time that you're comparing two sets of data to one another instead of looking at something compared to a larger population. So let's go ahead and figure out how we do that. So I'm going to give you some data here. I won't necessarily set up where these data are from. Of course, you will be getting data from something, but in this case, we're just going to work with the numbers, and I want you to do the following. All right, so first, we're going to find the mean for each group. We need to find the mean for each group in order for us to compare them to one another. Then, in order to calculate a t-test, we're going to also need the sums of squares for each group. So we're going to find SS1 and SS2. And this is going back a few chapters to calculate the sum of squares, but I want you to see how they're all related to one another and how you can actually do a t-test from raw data if you needed to. Next, we'll use those sums of squares in order to calculate our pooled variance, which you learned about in the lecture. And then I want you to calculate the estimated standard error. So keep in mind that we are calculating our estimated standard error because we don't have our population parameters. And so we're going to do that using our pooled variance. Finally, once you have all of that, you can actually run a t-test for independent samples to find if group 2 is significantly different from group 1. So here I'm not looking for a direction, I'm simply trying to see if they're different from one another. Okay, so I'm going to move these data from this table here into a larger table where I'll be conducting my calculations. So here we see the same numbers that we saw in the last slide. Group 1, that should say group 2, I apologize for that. Hopefully you can fix that on your notes. So the first thing that we're going to do is simply calculate our means. This is easy peasy stuff. You've been doing this for a while now. So I'm simply going to add up all of my scores and then divide by the number of scores I have. In this case, I have 8 for each group. So my sum for group 1 is 49, divide that by 8, and we get 6.125. For group 2, my sum is 48, divide that by 8, and we get an even number of 6. So far we can see that these means aren't that different, right? They're only a difference of 0.125, but as we now know from statistics, just looking at the numbers isn't going to tell us if they're significantly different from one another, and so that's what the t-test is going to tell us. Now, because I know that I'm going to be calculating my sums of squares, I'm going to go ahead and square each number and then add those up because I know I'm going to need that for my sum of squares formula, right? We're going to need to square this number here, and then we're also going to need to add up all of the squares of each number. So I'm going to go ahead and do that in this table because that will make it a lot easier for me later on. So as you can see, I'm simply squaring each number, right? We've done this millions of times, maybe not millions, but it felt like it, right? And then we're just going to add those up. So the sum of my squares here so far, sum of each squared x is 315. Okay, so we're going to use that in the formula for my sums of squares. And then I'm going to do the same thing for group 2. Here I managed to put the 2 there. We're going to square each number, add those up, and this time we get 304. So we're going to use this row here, these numbers here, to get to my sums of squares for the two groups. Okay, so hopefully you were able to do this on your own. We've been doing this for a long time, everybody, so this should seem like a cakewalk at this point. Okay, so I'm going to go ahead and find the sum of squares for each group. We're going to start with group number 1. And as you remember, this is going to be our sum of squares equation. I'm going to do it once for each group. So here we're going to add up all of our squared scores and add those up, which we just did in the last slide. And then we're going to square the sum of our scores here, right, slightly different calculation, and divide by the number in our group. In this case, that number is 8. So I'm just going to fill in all of those numbers. So we had 315 from the last slide for group 1 here. We had 49 for our sum of scores here. We're going to square that, and then n is 8. Okay, so I'm just filling in the numbers from the last slide. Okay, so in order to figure this out, we just go ahead and do the math. So 49 squared is 2,401. We're going to divide that by 8 and subtract it from 315. So 2,401 divided by 8 is 300.125. Okay, so we now have our sum of squares for group 1, which is 14.875. So that was pretty painless, I hope, for everybody. We're going to do the exact same process for the second group. So remember, we already calculated this number. We already have this number here, which we can square, and our n for group 2 is also 8. So I'm just going to plug those numbers in here. We had 304 here. We knew that the sum of x here is 48. We're just going to square that and then divide it by 8. So that is simply 288 divided by, 2,304 divided by 8 is 288. So our sum of squares here is 16. Okay, so now we have the sum of squares for both of our groups, which means that we can go ahead and figure out what our pooled variance is and then get to our estimated standard error. So I know that these are a lot of steps, right? We had to figure out our mean, we had to figure out our sums of squares. Again, I want you to see that you can figure out your t from the raw data. I want you to see how these are all connected to one another, and that you can, if need be, do all of this math. It just takes a while, but you guys know this stuff. All right, so let's use the numbers that we just came up with to get our pooled variance. So remember that the pooled variance looks just like this, very simple. We're just going to plug in our sum of squares we got for group 1, our sum of squares that we got for group 2, and then the degrees of freedom for both groups. Okay, so we're just going to plug in 14.875 plus 16. We got that from our last slide. And then the degrees of freedom for each group is 7, because remember, degrees of freedom is simply n minus 1. So when we go ahead and do that math, we get 30.875 on the top, 14 on the bottom, which gives us a pooled variance of 2.205. Okay, we're getting there, everybody, right? We got our sums of squares so that we could find our pooled variance, but our pooled variance is really to get to our estimated standard error. I know these are a lot of steps, but bear with me. So our estimated standard error is simply going to be, so many things popping up at once. Okay, just bear with me. It's our pooled variance here, right? We just plug that in here. And then our n for each group on the bottom, and then we're going to take the square root of that whole thing, okay? And that actually ends up being, if you add that all up, the square root of 0.551. You can go ahead and double check if you haven't done the math yet. And then that gives us an estimated standard error of 0.742. Whew. Okay, so we finally got to our estimated standard error, which, remember, this is the bottom of our t formula, right? This is the bottom of our t formula. So now we have everything that we need to calculate t, but let's go ahead and go through each step of our hypothesis test. Okay, so our hypothesis, our null hypothesis is always that there's no difference. So there's no difference between the treated population and the untreated population. We don't know which one is which in this case, but we know that there's something different about the two groups. And of course, our alternative hypothesis is that there is a significant difference between the two. So let's go ahead and put together our criteria. In this case, we're going to run a two-tailed test because we're just looking for a difference. We're not looking for direction. I didn't give you an alpha, which means that you should use the tried and true alpha of 0.05. When we are running a t-test for independent samples, our degrees of freedom is calculated by n1 plus n2 minus 2. So in this case, it's 8 plus 8 minus 2, and that gives us a degrees of freedom of 14, and that gives us a critical t of 2.145. So I'm going to show you that on the t distribution. So here we see that if we're doing a two-tailed test, 0.05, we have 14 degrees of freedom. That gives us a 2.145 here. Okay, so that's how I came up with that number. All right, so that's the t to beat. That is the t to beat. Okay, all right, and remember it can be a positive or a negative in that case. Sorry, I didn't write that down, but it can be positive or negative because we're doing a two-tailed test. Okay, so now we can finally calculate t, and we have all of the numbers that we need for that formula, right? So we need this difference here, which we can calculate because we already have our two means. This difference here, which is our null, right? And if our null is true, that means the difference between these two is 0. So we're going to put in 0 for that. And we just calculated our estimated standard error. So all we have to do is plug in. So our M1 minus our M2, right? That's at 6.125 minus 6. Our mu1 minus mu2, again, that's if our null is true, equals 0. And then our estimated standard error was a 0.742. Okay, so that means that RT is 0.125 divided by 0.742. That's not looking good, you guys. That's not looking good. So our T here is 0.168. Wah, wah. So we failed to reject the null in this case, so that small difference of 0.125 did not end up being a significant difference. But again, you won't know that unless you do all of the work, all right? Like I tell my third graders, math is like a set of stairs. Can't get to the top unless you take each step, all right? So I know it was a lot of steps in this case, but I hope that you were able to follow along, and even more so, I hope that you were able to calculate all of these on your own. If not, I suggest go back, get the original data, and then try and do it on your own. You have all of the answers here, so you can go ahead and double check to make sure that you can do it. Okay, so let's move on to the next practice problem, see if we can apply this to an actual study setup and not just to some raw numbers. All right, so the next practice problem I had you look at was about statistics. Okay, so let's assume that statistics is taught right after lunch when most people are sleepy and have just eaten. Perhaps if it was right before lunch, the amount of material retained would increase. So this is a key word, right? Increase here. That means we're probably going to do a one direction, right? T-test, not the band, T-test. Okay, so to test this hypothesis, a statistics professor randomly selects 30 people to participate in an experiment. One group of 16 students are taught stats right before lunch, and one group of students, of 14 students, are taught statistics right after lunch. Okay, so after 3 weeks of statistics, either before or after lunch, they're given a quiz to assess their statistics knowledge. So hopefully nothing else is different about these groups. They're randomly assigned to be taught either before or after lunch, and we're going to see if that time difference makes a difference in how well they learn their statistics. Okay, so what you're going to do is figure out if there is a significant, at an alpha of 0.01, better retention of statistics when they're taught before lunch than after lunch. And I also want you to figure out the effect size of this difference. So now I'm going to give you the data for these two groups, okay? So before lunch, the 16 students got about 16 correct on the statistics quiz. Their sum of squares is 43, so you don't have to figure out the sum of squares here. I gave it to you so that we can just get to the good stuff faster. Okay, group 2 is after lunch. They have 14 students. They got a mean of 13 on that same quiz, and their sum of squares is 32. So as we can already see, there is a difference. There's a difference between the two groups. It looks like the morning group got a few more correct, but again, we need to conduct a test before we can say that this is a significant difference and that students should take stats before lunch instead of after lunch. Okay, so let's go ahead and do the math. Our hypotheses are the null and alternative, always, right? So our our null is that the difference between these two populations, right, because these students are meant to represent the entire population of students taking statistics either before or after lunch, is that there's no difference. That's our null hypothesis. Our alternative hypothesis is that our morning group, group 1, does better than group 2, so that means that the difference is above 0, right? So that positive number being above 0 means that there's an increase in their scores, which is what the problem told us to figure out, whether there is an increase and whether that increase is significant. So let's go ahead and set our criteria. Our alpha from the problem is a 0.01. We're going to conduct a one-tailed test because we're looking for an increase in their stats quiz score. Our degrees of freedom here is n plus n1, so 16, plus n2, 14, minus 2. So remember your group 1n, group 2n, minus 2. That gives us 28 for our degrees of freedom. So let's go ahead and look at our t distribution. We're going to do a one-tailed test. So we look in the first row, an alpha of 0.01, and we have 28 degrees of freedom. I always have a little bit of trouble here. We have a 2.467. Okay, let's make sure that's what we have over here. Yes, so our critical T, what we have to surpass is 2.467, only in the positive direction because we're only conducting a one-tailed test. Okay, so now we're going to calculate T. We're going to have to go to a whole different slide because it's going to take a little bit of room. All right, so let's go ahead and figure out our T. All right, so the first thing we have to do, always, if it's not given to us, is find our pooled variance. Remember, you are used to S squared. That's variance. P just means pooled, combined, put together, right? Okay, so we have all these numbers. I gave you your sum of squares for group 1, I gave you your sum of squares for group 2, and of course we can calculate our degrees of freedom for both groups because it's simply n minus 1. So I went ahead and plopped those numbers in there. So 43 was our sum of squares for group 1, 32 was our sum of squares for group 2, 15 is our degrees of freedom for group 1, 16 minus 1, 13 is our degrees of freedom for group 2, 14 minus 1. That gives us 75 on the top divided by 28 on the bottom, gives us a pooled variance of 2.679. Easy peasy, guys. Easy peasy. All right, it's just plopping in numbers. Okay, so next we have to figure out our estimated standard error using right, that pooled variance in this case. So we plop in our pooled variance, 2.679, into both of these, and then we're using n, right? We're using n. So in this case, 16 and 14, and that gives us 0.598. There should be a square root right here. That's why I'm like, what's happening here? There should be a square root right here, and then this, so 1.6. So you add 0.167 plus 0.191, you square root that, right? You take the square root of that and you get 0.598. And that is our estimated standard error for both groups going on, okay? Because we used our pooled variance. Then finally, we calculate our T. All right, so it gave you the M's. We know that our mu1 minus mu2 is what? I hope I heard some zeros. Okay, so mu1 minus mu2 is 0. We just calculated, there it is, our estimated standard error. So that means that we have 16 minus 13, right, minus 0. We have 3 on the top, and we're going to divide that by 0.598. That gives us a T of 5.017. Everybody check my math, okay? Check my math. One person. Okay, but that T looks good. T looks awesome, right? It's definitely in our critical region. We reject the null. Woo woo, woo woo, party time. That means you should be taking stats before lunch. All right, let's calculate our effect size. We're going to use R squared in this case. R squared is simply, don't forget, T squared on the top, T squared plus your degrees of freedom on the bottom, we're going to calculate those numbers, gives us an R squared of 0.473. That means we can explain almost half of the variability in our dependent variable. That's a lot. That is a lot. So remember, the two groups wouldn't have done exactly the same, right? Just because of sampling error and all that good stuff. So we can explain half of their difference due to being morning over afternoon time. Okay, so we've done a lot. We still have one more. Let's go on to the next practice problem. Okay, so our next problem has to do with college campus drinking, which a lot of campuses are very interested in. So let's say that in a study of college campus drinking, 2 samples of 8 students were given information about the hazards of drinking. In the first group, the information was presented in a pamphlet. In the second group, the same information was presented in a panel of college students. Later, the samples were observed to see how many drinks they consumed at a party. So we'll go ahead and assume that there was a research assistant who was on the sly, who was counting how many drinks they had at said party. So do the data indicate that there is a significant difference in the amount of drinking that the 2 samples engaged in? So that word difference should be cluing you in to whether this is going to be a one-tailed or two-tailed test. So we're not looking for a direction, we're just looking for a difference. In other words, do the data indicate that the delivery method of information on the hazards of drinking, so pamphlet versus panel, had a significant impact on drinking behaviors? Okay, so this is what the SLY RA found. So for the 8 participants who had the panel, they drank on average 6 drinks. That's a whole heck of a lot, you guys. So that's a little crazy. So maybe the panel backfired. We don't know. And then we found that they had a variance of 3.43. Now, don't get too worried. I know that we've been working with either raw data or I've given you your sum of squares and you're like, I have variance. What am I supposed to do with that? But, well, you know it. It's in there in your brain. Okay, so we will figure it out. The pamphlet group only had 3 drinks on average. Still actually a little high. And so they had a variance of 2.29. So we're going to use these data to figure out if there's a difference in how students reacted to these 2 methods of delivery for the hazards of drinking. So let's go ahead and figure out what we should do with these data. Our null hypothesis is that there's no difference between the methods. So students are drinking the same whether they get the information from a pamphlet or from a panel. Of course, our alternative hypothesis is that students would drink different amounts depending on how they got the information. So we're going to use an alpha of 0.05, two-tailed because we're only looking for a difference. Our degrees of freedom in this case is 8 plus 8 minus 2, which is 14. And our critical T, come in. Our critical T here is 2.145, either positive or negative, right? Because we're going to either side, we don't know where the difference is going to be. Okay, so that stuff's easy. Now we're going to calculate T. All right, so how are we going to do that if we have variance? We don't have sums of squares. All right, you guys, I'm going to blow your mind. So if we know our variance, we can get to our sums of squares. Why? Because we know that variance is simply sum of squares over n minus 1, right? So that means if we just move this n minus 1 over here, our sum of squares is simply our variance multiplied by n minus 1. What? I know. You guys, it's all there for you. It's all there. All right, so go ahead and calculate your sum of squares for each group. For our first group, their variance was 3.43. They had 8 students, so their n minus 1 is 7. That gives us a sum of squares of 24.01. Our second group had a variance of 2.29. Again, we're going to multiply that by 7. That gives us a sum of squares of 16.03. Now we can just plug and play. All right, so let's go ahead and figure out our pooled variance, right? Because now we have the sum of squares for each group, and of course we have our degrees of freedom for each group. So I'm going to go ahead and plug those in. So 24.01 for group 1, 16.03 for group 2, 7 plus 7, that's the degrees of freedom for each group, and that gives us a pooled variance of 2.86. Nice. Now we're going to go ahead and figure out our estimated standard error. Your eyes aren't playing a trick on you. That's a little, it's a little blurry. But you should know it by now. You should know it. You shouldn't even have to look anymore at the estimated standard error formula. So here we're just going to plop 2.86 into here, divide each one by 8. That gives us the estimated standard error of 0.846. Okay? All right. And then finally, we plug all these bad boys in to our T formula. So remember, our first group drank 6. Our second group drank 0. Or sorry, 3. So 6 minus 3 here. And then our null hypothesis here is that the difference between mu1 and mu2 is 0. Okay, so here we have 6 minus 3. This whole thing is going to be 0. We just figured our estimated standard error. It's right here. So go ahead and plug that in. We have 6 drinks minus 3 drinks minus our null. We're comparing it to our null. And then we divide that whole thing by 0.846. That gives us a T of 3.546. So this means that students in the panel condition drank significantly more than students in the pamphlet condition. So perhaps having a panel is actually not the best idea. And this actually would make a little bit of sense because often when you get students saying things like, oh, I used to binge drink all the time and now I don't because I learned my lesson, students end up thinking, oh, I'll do the same thing. I'll binge drink and then I'll learn my lesson and I'll be fine. So it's not actually great to do it that way. Okay, so what does this mean for us? Reject the null. Party time. I hope everyone's doing their happy dance. I'm doing my happy dance. All right, so that is 3 awesome practice problems for your independent samples. Hopefully you were able to follow along. Again, if these are not the numbers you got or if I went really fast, go ahead and start at the beginning with those practice problems and try and calculate them yourself so that you know what to do. All right, so hopefully now you understand how to compare two groups that represent 2 populations to each other. This is a very, very, very popular method of doing behavioral research. So this is a really important t-test to know how to do. Okay, hope everyone is enjoying their time in T-Town, and I will see you all next time.